we are going to continue on using our new components way of thinking about some force situations that we've encountered in the past in grade 11. So in grade 11, everything that we did, all of the situations that we encountered were all level surface situations. You may have noticed that when you were going through questions, they always said, on a level surface, so-and-so is being pulled along, or whatever the situation was. And then if you were in my class, I told you that in grade 12, we're going to take your level surfaces and put them on an angle. And here we are taking your level surface and putting it on an angle. Inclined planes just means a ramp. That's all an inclined plane is. A plane is a surface of some kind, and an inclined plane is one that's inclined. What do you know? So we're going to have to kind of change up how we use components. So before, the x-axis was perfectly horizontal like this. On an inclined plane, we're going to call the x-axis like this. It'll be the parallel component along the ramp. And the y-axis, that one, will be the perpendicular component to the ramp. Okay, it'll make more sense in the example. So here we go. A 100 kilogram mass is on a frictionless incline of 25 degrees. To keep it from accelerating down the slope at too great a rate, a person exerts a force of 400 newtons directed up the incline. Calculate the net force on the mass. So here is our incline of 25 degrees. Maybe that's a little more than 25 degrees, but we'll go with it. And then you have a 100 kilogram mass. So here's our mass. To keep it from accelerating down the slope at too great a rate, a person exerts a force of 400 newtons. So I'm going to grab a different color here, and then we're going to draw some forces up here. So someone is exerting a force up the incline. We're going to call that FA, or the applied force. Again, you could call it pushing force, whatever. Maybe you're going to assume that that's a rope and you want to call it a tension force. Sure. We also have the force of gravity. And the force of gravity pulls straight down. In this case, it is not going to be a y force, because a y force is going to be perpendicular to the slope. Okay? And then we have a normal force, and the normal force is perpendicular to the slope, because by definition, normal means perpendicular. Okay, so you get the normal force pushing away from the slope. And then you also might have friction in some cases, but in this one you do not. It says it's a frictionless incline of 25 degrees. Okay, now we are wanting to look at the parallel forces, okay, because we're trying to figure out what the net force on the mass is, and because this box is not accelerating into the ramp, give me a moment here, the box is not accelerating into the ramp this way, right? It's not getting sucked through the ramp, and it's not being tossed off the ramp this way. That means that the y forces are balanced. So let's get rid of that. It's only the x forces that may not be balanced. Okay, so we want to add up the applied force, which is this one over here, and we want to add up whatever force is causing it to fall down the ramp or to move down the ramp. Okay, and it doesn't look like anything is pulling it down the ramp, but our force of gravity is not directed perfectly x and y, right? So if this is our x and y axis, here's our y axis, and here's our x axis. We can see that our applied force is an x force perfectly. Our normal force is a y force perfectly, but the force of gravity is not x or y. It is a combination of the two. And so what we need to do at this point is split our force of gravity into a parallel and perpendicular component. Okay, so we've got the force of gravity total over there, and that is made up of force of gravity perpendicular, because it's perpendicular to the ramp, We can call that Fy, because that's on our new y-axis. And we can also split it into Fx, which is our parallel component. Now sometimes you'll see this written as F parallel and F perpendicular, and sometimes I will flip between those as well. But for this particular example, we're going to do Fx and Fy. We've just changed what the x and y axis are. Okay, so we know that this angle over here is the same as this angle over here. How did I know that? So if we were on a level surface, let's just say we took this entire thing and we just tilted it back down. So it used to be like this, we tilted it back down. What is the difference between the angle of the force of gravity and the plane? It's 90 degrees, right? So let me just give you a little example here. This is now a level surface. Our force of gravity is pulling down, and the angle that the ground is tilted up at is nothing. It's 0 degrees. Okay, and so the angle between the force of gravity and the inclined plane is 90 degrees. So if I looked at this one over here, this is 25 degrees. The angle between my plane and Fy should still be 90 degrees. And we can see that it is. That's this right over here. Okay, so that's still 90 degrees. And now we just have to think about the difference between where the plane is over here, the difference between where the plane is and where horizontal is, right over there, is 25 degrees. And so also the difference between Fy and normal force of gravity, this force of gravity over here, is also 25 degrees. Okay? And so even if that explanation didn't work very well for you, you can just remember that this angle in here matches the angle of the inclined plane. Okay, so that's also 25 degrees. So now we need to figure out what is that Fx part that's pulling the box down the plane. So Fx is the opposite side compared to our angle, and so we're going to use sine, right? So sine of 25 degrees is Fx, that's the opposite side, divided by force of gravity in total. And so we're going to multiply by the force of gravity, which is mg, in order to figure out the x force of gravity. So often I'll call this Fgx, especially because sometimes there's going to be a different x force also involved here. But for now, it's okay to call it just Fx because it's the only other x force that's pulling it down the ramp. Okay, so now we're going to solve for Fx, and that is a mass of 100 kilograms times 9.8 meters per second squared times the sine of 25 degrees. That's our x component of gravity. And we also want to, in order to figure out what the total is, we're going to subtract from that 400 newtons directed up the incline. Okay, so we're using F net equals ma, but in this case we're just trying to figure out what F net is. So what's the total of all the forces? So F net is Fgx minus Fa. So here we've got 100 kilograms times 9.8 meters per second squared times the sine of 25 degrees minus 400 newtons. And altogether, that should get you 14.2 newtons, and that's down the ramp. Then part B asks us to calculate the acceleration. We've done most of that work already, and so there isn't much more to it. We just now have to remember that we're using F net equals ma to figure out that acceleration, and so the acceleration is F net divided by m, with an extra squiggle on the side of the m. So our acceleration is 14.2 newtons divided by 100 kilograms, which is 0.142 meters per second squared, also down the ramp. Okay, that part hopefully was not difficult. The part that you're going to need to get used to is how to write Fx and Fy forces, how to account for the x and y forces in an inclined plane situation. And I highly recommend drawing the free body diagram. This giant hideous thing, I mean beautiful thing, draw that thing in order to make sure that you've got all the forces accounted for. Okay, it'll also help you to get your mind around this triangle, this components triangle that happens with the force of gravity. Example 2. A 20 kilogram mass is on an incline of 15 degrees. A force of 150 newtons is applied to the mass directed up the incline, and the mass is accelerating up the incline even though 80 newtons of friction is acting on the mass. Calculate the acceleration. Here's our 15-degree inclined plane with our mass. Actually, let me draw in the 15 newtons there. 15 degrees there. And then I'll grab a different color. So then we have a force directed up the incline. That's Fa. We've got friction pulling down the incline. And then we also have our force of gravity triangle. So there's the total force of gravity. And then we're going to split that into its components. So here's our perpendicular component, or FGY. And here's our parallel component, or FGX. Okay, remember that this angle here is also 15 degrees. It matches the angle of the incline. And so we're supposed to figure out the acceleration of the mass. So we're going to use F net equals ma to figure that out. It's the only tool that we have to figure out acceleration. In this case, we just need to account for yet one more force. Okay, so F net is now not only the applied force and FGY, or FGX, sorry, it's also the force of friction. So it's accelerating up the incline. I'm going to make the applied force positive then, and I'm going to make the other two negative. So that's FGX and the force of friction equals ma. Now we can first of all rearrange the formula if we want to, or we can expand all the pieces first. It really doesn't matter. You can do them at the same time if you want to. So I know the applied force, I know the force of friction, so I don't actually need to expand the force of friction into its formula this time, but you may need to, shouldn't say may, you will need to in some of the practice and problem solving I'll ask you to do. So really only FGX is the thing that needs to be expanded into its pieces. So this is 150 newtons. This FGX is the opposite side, and so it is mg times the sine of 15 degrees. That's going to be really common. And we are just told what friction is, so we can just put in the 80 newtons there as well. And that is equal to 20 kilograms times the acceleration. Now we're going to divide by that 20 kilograms to get the acceleration by itself. And when we do all of that stuff, so here, let me just write down that final formula, minus 20 kilograms times 9.8 meters per second squared times the sine of 15 degrees minus 80 newtons. All of that divided by 20 kilograms. That gives you the acceleration that we're going for. And when you do that whole calculation, you should get 0.96 meters per second squared. That's a positive answer. So that's up the ramp. Now we expected that because that's what the question says. It's accelerating up the ramp. And so we designed our whole question around that, all of the positives and negatives everywhere. So it's no surprise that it works out that way, but it should work out that way.